This video demonstrates the simulation of three-dimensional water flow, featuring 2 measured water levels and 1 pumping well. Groundwater is continuously extracted at a constant rate from the center of the region. The simulation aims to assess how the groundwater level changes over time. The results will illustrate how the water flow, including its velocity and direction, changes throughout the simulation period. The simulation consists of 6 main steps. First, in a new project, we use the Geometry Mesh GUI to build the geometric model and generate the mesh, as well as to define the spatial locations of initial and boundary conditions. Next, in the Model Parameter Input and Simulation GUI, we import the mesh and spatial group information, configure the initial or boundary conditions with specific parameter values, and then run the simulation process. Finally, the simulation result file needs to be decoded and converted to the desired format, and it can then be visualized using the Visualization GUI. We need a central project in the THMC platform to cascade and manage all related data. To begin, create a new project by entering a desired project name and selecting THMC 3D, then click Confirm. Next, open Geometry Mesh GUI. Click File and create a new solution. A single project supports multiple solutions. However, in this case, we use the default solution name. Click Create New to complete the process. To build the geometry mesh, start by creating a square or a circular polygon, depending on your modeling needs. Enter the dimensions according to your site parameters. In this example, the site is 100 meters in width and 50 meters in height. At this stage, you can also adjust the mesh density. The smaller the value, the higher the mesh resolution. Once the parameters are set, click Preview then Create. If you're modeling a tunnel or hollow structure, create an additional polygon and check the hollow option. Next, click the Mesh Generator icon. In this step, we create a two-dimensional mesh. The mesh type is set to triangle. The next step is processing the borehole data. Click 3D Setting, then open Terrain Editor. Click Import Borehole and select the file that contains coordinate data. You can adjust the borehole marker size under Canvas Settings to improve visibility. To update the mesh, click the Mesh Generator icon and click Triangle again. This action will regenerate the corresponding mesh nodes to align with the borehole locations. The next step is to define the depth of the geological layers. Click 3D Setting to open Depth Editor, and you can see 3 panels in the window. Start with the first panel, insert your number of geometry layers, and the number of materials. Set the stretch according to your site. The stretch count refers to the number of horizontal slices at this geometry layer, which helps generate mesh elements with finer resolution in the vertical direction. In this case, we set the stretch count as 3, 4, and 3. This means the top geometry layer is divided into 4 mesh layers, the middle geometry layer into 5 mesh layers, and the bottom geometry layer into 4 mesh layers. Moving on to the second panel, set the geometry layer for each overland surface domain. Now we set the node depth in the third panel. You can select elevation or offset from surface, depending on your data. Then, input the depth values for each node across the different geometry layers. To quickly apply a value to the entire column, select the target layer, enter the desired depth, and click Update. You can also edit individual nodes to match specific terrain features. Click the Mesh Generator icon, then select Triangle Prism to generate a three-dimensional mesh. Left-click to rotate the view, right-click to zoom in and out, and click the scroll wheel to pan. You can set the view direction from the panel above. Now the mesh is complete. The next step is to set spatial location groups for initial and boundary conditions. First, set boundary nodes into groups. Click Select Nodes and select the left boundary. You can see the number of nodes on the left. There are 55 nodes for the left boundary in this demonstration. Click Create Group. Select Hydrological as the simulation category and choose Dirichlet as the condition type for the constant head boundary. Click Assign Group Name and edit the group name to something recognizable. Make sure the point count is correct and click Apply and Close. The group can now be found under Conditions. Click the Delete All Selected icon and repeat the steps for the right boundary. Next, select the pumping well. Please note that the condition name is point source sink. Lastly, select all nodes. This is for setting the initial water level. The condition name should be initial. You can recheck the spatial group setting results. There should be 4 groups under conditions after all the steps are done. Finally, save all setting result in menu by click File, then Save Solution, and click OK. The process in this module is complete. Open Model Parameter Input and Simulation GUI. On the top left, click the Mesh Import and Boundary Data icon and click Import. In the Module section, select only Fluid Flow. Then, choose Transient and make sure the Steady option is unchecked if it's selected. Set up the time according to your needs. Next, we set the material. Select the material for each layer ID. Recall that the material count was set to 3 earlier. You can drag the materials to edit the sequence and edit the characteristics of each material below. Click Save. Next, set up the initial and boundary conditions. Choose Hydrological/Initial Condition under the spatial type and click Add. Select the domain, which includes all nodes. The initial water pressure in this case is set to 0. Following, choose Dirichlet boundary under the spatial type. Start by configuring the left boundary, edit the profile by adding a new profile name and setting the time range from 0, which marks the start of the simulation, to 1.0 e plus 38, which represents an effectively infinite duration. Click Save. Next is the right boundary. Add a new profile, edit the head, and save. Lastly, set up point source sink, which is the pumping well. Add a new profile and enter the pumping rate. Save the progress. You can now execute the simulation by clicking Start at the top. When the process is complete, the status will show complete. Open the Visualization GUI and click the Add icon to decode the simulation result for visualization. Make sure all checkboxes below are selected. Then, choose the file you want to convert. Click the Start icon. After selecting PowerView, click Open. The software PowerView will open automatically. In the top panel, a drop-down menu allows you to select from various physical parameters. Click Play to observe the changes over time. This is the total head demonstration. Let's watch it again. This is the velocity demonstration. Let's watch it again. This concludes the demonstration. Thank you for your attention.